This is my screencast for Chapter 5. I think I might also do an Illuminate Live of this, but for now I'm just doing the screencast. So just one chapter this week. I purposely gave an entire week to Chapter 5. Same thing with Chapter 6. They're difficult chapters, so let's dive right in. So the first part, whether something is a particle or a wave, we seem to have noticed some weird stuff in the previous chapter that electrons, for example, have a wavelength, which because they exhibit interference when they go through double slits, for example. So I think the author does a really interesting thing here, where he chooses the word quantum and tries to stick with that. If you look in the errata for this book, a lot of them is changing the word electron to quantum, because he thinks that by calling it a particle, that, well, you're biasing it a little bit. So we're going to try to use this term for everything, and I'll try to stick with that. The single quantum interference. This is really the big deal that, of course, is talked about in the YouTube video. Again, I just linked it here again. You've probably seen it because I've told you to watch it twice. But one more time to watch it. I think it does a really good job explaining what you expect with macroscopic particles like bullets, waves, which we hit way back in Chapter 1, and then these weird quantums, although I'm pretty sure the video uses the word electrons. So the big deal here is what exactly happens when you reduce the intensity to just one quantum at a time. If you're using light, you use maybe filters, lots and lots of filters to make the laser light to come in, one photon at a time. I actually attended a conference once where someone described an experiment with zeptojoules of energy. That's like 10 to the minus 21 joules of energy. And he was explaining how he had measured the polarization of this particular light. And someone said, well, that's such an amazingly small amount of energy. What does that mean? And it turns out that it was one photon every 10 shots. So they hardly ever actually had any signal coming through this thing, and they had to sit there and wait and collect it. Also interesting, the very next talk, I think, was about a petawatt laser system, and so it was something like 30 orders of magnitude change from one talk to the next. Pretty interesting. I will say that this interference application on this website here, let's see, you scroll down to Q, is pretty good. It lets you monkey around with stuff. I'm not going to load it because it seems to slow the screencast down, but I will show you one of the movies that I've made here. So this is just a simulation, keep in mind, trying to show you what happens when you shoot these quantums through a double slit experiment. Notice that dots show up. When you shoot one quantum shows up somewhere on the screen. But what happens after you let it go for a long time is you notice that they seem not to fall in certain locations. So for example, right here you never see a quantum, or here, maybe right here, you see a bunch. And so when you see a histogram of this, which is, by the way, what the other program does, you get a sense of somehow the quantums knew that it needs to make an interference pattern. So what are the implications? Well, first of all, this is not a classical thing. There's something very, very strange going on. It's absolutely not like shooting BBs through a double slit, so there's definitely something weird. There are a few different explanations. The first is that the quantums are interfering. If you shoot enough of them at a time, maybe one quantum goes through one slit, another goes through the other slit, and then they somehow interfere with each other and don't allow each other to go into the dark spots. But that's the whole notion of turning your laser or your electron gun so far down that there's just no chance of them having interacting like that. So the second is that somehow the particle goes, it splits, it experiences both slits, and then somehow comes back together again. And in the next section we'll talk about that for a second. I think that it's just very, very weird to realize that the interference pattern that you see is dependent on the spacing of the slits. So clearly, if a particle just goes through one of the slits, how would it even know where the other slit is? And the interference pattern is determined by the spacing of the slits. So you need to know where both of them are. Okay, so the next section, I think, is a really, really important one. You should read it a couple of times. Essentially what happens in the double slit is if you set up something to be able to detect which slit the quantum goes through. And there are ways to do this, right? You could put little other electrons, pepper them around, and then if an electron goes through a slit, the other electrons will get smacked. Or if you're using photons, you can also put just some electrons, pepper them in there. and if the electron goes through, it'll smack the electron. Why would you use electrons? Because they're so small that one would hope that it wouldn't adjust the trajectory. But it just seems like if you really try to answer this question, which slit did it go through? And let me be more specific about that. The question you are asking is, hey, particle, not wave, hey, particle, which slit did you go through? If you get an answer to that question, then the interference pattern goes away, or the wave issue goes away. I want to be careful here. It says more about what a measurement actually is than quantums being weird. Okay, so the measurement, the act of measurement was the new thing here in the quantum world. We usually like to say that, for example, when a radar gun measures your car, it measures the speed of the car, but it doesn't actually speed up or slow your car down. Well, actually it does, right? It's got to use little radar photons that hit your car and transfer momentum. But it's usually such a negligible effect that we say that you can certainly build equipment that can make a measurement that doesn't change things. Well, in the quantum world, everything is so small that that is impossible. You can't make a measurement without weird things happening. As we move on to later chapters, what we're going to say is that every measurement forces a collapse of the wave function. So by saying, hey, which slit are you going through, it forces it to collapse. It says, oh, you're asking me that question? Okay, well then I'll actually choose one and go through it. But that collapse then screws up the interference pattern on the screen. And we're definitely going to talk a lot more about that in Chapter 6. Okay, so then we get into spin experiments, and I think that the author has made an interesting choice here. If you read a lot of the quantum books out there, very rarely will you see, at an introductory level anyways, the Stern-Gerlach experiment. The reason is because the physics of the actual experiment involves spin, it involves some pretty complicated stuff, and that's why people don't do it. The reason our author did do it is he sort of glosses over all the spin. He says, look, here's just this weird experiment. It really only has two outcomes. The particle, the quantum, either comes out over here or it comes out over there. So he thinks that it's actually a whole lot simpler than, say, a double slit experiment. Now, the double slit experiment's easy to explain. It's just wave interference, that kind of stuff. But there's just hundreds, thousands, millions of possible things that the particle can do. If you go back to the movie that I showed you, every single quantum has lots of different places that it can show up. So the author, in fact, talks somewhere in the introduction of this book about his choice in the second edition of the book to just do the Stern-Gerlach experiment, even though it means sort of having to gloss over some hard physics. So what are we saying here? Well, let's go to, I've got a few different things. By the way, this simulation here is very, very nice. Also, oh, I guess I didn't put a link to it. The same place here, if you go down to, I'm sorry, here, this Spins 1.0 is an excellent, excellent program, and it's going to come in very, very handy in Chapter 6. In fact, if I'm not mistaken, in Chapter 6 we're going to be using that program to do some homework. There's lots of different ways to go, but again, these simulations just don't seem to run that well when I'm doing the screencasting, so I'm not able to do it. But let's take a look at some pictures here. You have an oven. This is creating the quantums, and they head out and they experience a very strange magnetic field. A sharp point and a big old fat pole here. What that means is the magnetic field is much stronger at the top than it is on the bottom. So you get this, you get a magnetic field whose strength is changing. Now, when you dump, say, a compass needle in a magnetic field, like the Earth's, for example, it'll spin, it'll rotate around, no problem. But when it's in a non-uniform field, what happens is magnets will always group towards where this field is the strongest. They tend to head towards where the field is strongest. That's one pseudo kind of explanation of the northern lights, that the charged particles coming from the sun go to where the field is strongest, at the poles. It also explains when you dump iron filings on a magnet that they all seem to clump at the ends. So one would expect, therefore, that you would get, if there were some magnet aspects to these quantums, that you'd get this effect. Well, electrons have spin, and that spin can point in any direction. It's essentially the direction of the line pointing from the south pole to the north pole of the thing. But the classical explanation says that, well, if these electrons, they came from an oven, totally random, they should be pointed in all kinds of directions. So some should go up and some should go down. And so the classical explanation is sort of a big old blob. But what you actually get is a clear separation. About half of them are pointed up, half are pointed down. So you only get two possible choices in these Stern-Gerlach experiments. Let's see here. Wikipedia, I thought, had a nice explanation as well. I guess this picture here, let me make it bigger. So you can see, it's roughly the same thing, I guess. So there's nothing new there. So the big deal here is that we just have two possible outcomes. When you use one of the devices to measure it, the device essentially says, hey, incoming electron, your spin is roughly how close to my alignment? And the electron says, oh, I'm about theta away from your axis. And the thing says, oh, great, wonderful, wonderful. Well, I'm sorry, but you must become either with me or against me, aligned to me or anti-aligned to me. And the electron says, oh, gosh, do I really have to? And the machine says, hey, this is the quantum world. This is how it works. And so it does. It becomes either aligned or anti-aligned. The chances of it becoming aligned are cosine squared 1/2 theta. The chances of it becoming anti-aligned are sine squared 1/2 theta. So let me be very, very clear. Let's say you have a system that's wanting to find electrons that are straight up and down. If something comes along and it's, let's say, left and right, it comes in and the thing says, I'm sorry, you need to convert to either with me or against me. And the electron says, do I have to? And it figures out the angle. In this case, it would be 90 degrees. Well, 90 divided by 2 is 45. Interestingly, cosine squared of 45 and sine squared of 45 is about the same. So it's like a coin toss. Sometimes it collapses up here, and sometimes it collapses down there. Well, what if you send in something that is actually perfectly aligned straight up and down with the axis of the device that wants things to be straight up and down? Well, then it says, I'm sorry, you need to collapse to me. And the thing says, well, I already am one of you. Oh, okay. Well, does that work mathematically? Sure. Well, if theta is 0, then cosine squared is 1. It stays aligned. These devices are self-consistent. It means if you make a measurement and you check it again and again and again without letting anything else happen, you'll keep getting the same answer. So at first it seems like it's this random change these electrons have to go through, but if you keep asking the same question, it won't have to change anymore. And then there's this very, very weird result that the change happens only if you bother to actually record it. Because if you force it to go through a machine but take both outputs of the machine and sort of splice them back together again, like, let's see, we've got an example way down here. Here we go. I believe we have an example. Oh, they don't show it, darn it. But if you take the two outputs of a device and mix them together, then it is as if you did not even make the measurement. So you have to be very careful about this, forcing the change, forcing the electron to change. It's only if you actually record the result. Now, I said the author made kind of an interesting choice to do this. There are lots and lots of simple examples that do it. I actually wrote a book for the previous versions of this class where I focused on light polarization. So when you send light through a polarizer, right, we usually say to our students, oh, well, it's the component of the light that's along the axis of the polarizer. Well, but what if you send a photon in? It either makes it through or it doesn't. So it's two choices, makes it through or doesn't. Even reflection works this way. When light hits a window, we like to say that 4% of the light bounces back again. 4% is for standard glass windows. But now shine, 100,000 photons on it. Well, 4% of 100,000 is 400. On average, you expect 400 photons to bounce back. But here's the kicker. Do it one photon at a time. Really, really dim. If you send one photon at a time, it either comes back or it keeps going. And it seems to make a random choice. And so one photon at a time seems random, but when you collect all the results, weird. Exactly the right percentage comes out. Lastly, let me cover these complex numbers here. There we go. Wikipedia has a nice description of the basics of how complex numbers work. I'll let you read that. I'm not even going to click on it. There's a few things I want to do. We're going to be doing this interestingly shaped thing quite a bit. You essentially ask, hey, current state of life, or I guess let's say W is what we think the electron is right now. how much of you is like this other state, this maybe the state that the device likes? How much of you is like it? So it's essentially asking questions that gets at answers like this. And the way you do it, this usually has a bunch of components, like a vector. And so this, you take these components, the u components, and you complex conjugate all of them, and you multiply them with their pair. So 1 goes with 1, 2 goes with 2, with the component from w, but w does not have a star on it. So we're going to be doing this a lot, and you have some homework on that. Normalization is a big deal. All that means is that you have a vector whose if you do it to itself, hey, how much of you is like me? All of you is like me. Now, not all vectors that you just arbitrarily wrote down have this quality, but you can always divide the vector through by some constant to force this to be true, and we call that normalization. So it does seem odd that this section is in this chapter, but he's clearly setting us up for something. Why are we using this? Well, the quantum universe is weird. Apparently the universe is complex, meaning complex numbers, not just hard. It's how the universe works. All of this weird probability stuff, this collapse, all of that stuff seems to work with complex numbers. In fact, if you look at the Schrödinger equation, which we will in a few chapters, it actually has the letter I in it. And so, wait a minute, I thought we lived in the real world. Well, it is very strange. It seems like everything in the universe has two pieces to it, a real part and an imaginary part. But when we do experiments, we can only get access to one piece. Unfortunately, it's not so much that we see the real part. Rather, we see the magnitude squared of the wave function. In other words, essentially this thing squared. And so we're going to be doing a lot more of that in subsequent chapters.